Okay, last we left off, we were talking about buffers. Okay, so buffers are basically when you kind of use a weak acid to kind of let's see, that's right. You're using a weak acid with like a strong base, and you're kind of setting it up so that that weak acid won't be too affected by the addition of the strong base, right? So you'll have a wide range where you can add a base and it won't change the pH. It'll have little effect on the pH until you reach a certain point, okay? And that's vice versa as well. So if you have a weak base with a strong acid, same thing happens. Okay, so over a large range, you basically make it pretty much pH resistant. Okay, so various buffers, various weak acids or weak bases, they have optimal ranges that they work in. And because they sit there, they work in different ranges. So you can sit there and set an acid, say you want to try to keep your pH in a range that is around 3, a pH of 3, then you would select a buffer that would be ideal for that. So kind of like acetic acid or something like that. Okay, you guys kind of get that. Okay, so here's an example. It's the way that we're looking at this. This is going to behave it's going to be exactly the same thing as we've been doing with equilibrium problems in general. It's always going to be products over the reactants, and that's going to equal our equilibrium constant. So that isn't going to change, okay? So let me give you an example of a problem that you may see that's a buffering problem. Okay, calculate the pH of a buffer solution with 0.500 molar lactic acid and 0.115 molar sodium lactate with a Ka of 1.38 times 10 to the minus 4. Okay, so if we think about this problem here, right, we have acid. What is our acid in this case? Lactic acid. Okay, so we have lactic acid as our acid. Let me guess. What are you guys seeing? Are you seeing my two little screens?
Yeah.
Thank you for telling me. Guys are evil. Decided. So we have lactic acid, and lactic acid is going to be with water, right? So what is going to be the result of that? Here's our lactic acid plus water. What is going to be the result?
Would you have the hydronium?
You'll have the hydronium.
And the lactate, the C3H5.
That's right, the lactate. Okay, so in this situation, if we did our ice table, let's see, I need to make room for our ice table. It's going to do my ice table down here. So we have, and use La for lactic acid. going to use H3O4. And then for lactate, we'll use, just type in lactate. So we have ice. So in the problem, what is our initial concentration of lactic acid?
The 0.500 m.
Okay. Now the sodium lactate, what it does, it acts like initial concentration, but of lactate. So we know that sodium, when we put sodium with anything, sodium always wants to dissolve. So as soon as you put in solution, it's going to dissolve. You're going to get the sodium ion and you're going to get the lactate ion immediately, right? So in other words, that sodium is just going to be acting as a spectator. So in this case, we're kind of initially spiking the solution with lactate by using what we have there. And since if we looked at the concentration, it's a 1-to-1 ratio between the sodium and the lactate. So then it would be the same molar concentration. Make sense?
Yes.
Yes.
Okay. So the change is going to be represented by our typical X. So if X is going to be our products and we're making X, then what's going to be happening on the reactant side?
Minus X.
Minus X. Okay, so now we have 0.500 minus X for our equilibrium. This guy is just going to be X. And this guy is going to be 0.115 minus X. Okay? With me so far?
Yes.
Okay. So then if we have our equilibrium constant, Ka, is going to equal this is where you guys chime in. What was that?
Is the products over reactants?
Products or the reactant. It hasn't changed yet, right? Good job, Selena. Keep it up. I'm going to be, let's see, 3, H5, O3 minus. Okay. I'm going to be a lazy Bob and put lactic acid, La. Okay. So if we go ahead and start plugging in our values for things, we just use what we have at equilibrium, right? So up top, what are we going to have for the hydronium ion? Okay, X times, what are we going to have for the lactate?
The 0.115 minus X.
0.115 minus X. And then what are we going to have on the bottom?
The 0.500 m minus X.
Okay. And so that's going to be equal to our Ka, which is 1.38 times 10 to the -4. So if we go ahead and work this guy out, we get 0.115x minus x squared. Oh, actually, that should be plus x squared. My bad. Because that's a positive value, so it should be a plus. Over, actually, we'll just go ahead and do the multiplication on the other side. (1.38) times 10 to the -4 times 0.500 minus x. One point. Oops, 1.38. So we'll have 6.90 times 10 to the -5 minus 1.38 times 10 to the -4 x. So we're going to bring this all over. Going to bring it all over to the other side. So we'll end up with, change it around a little bit so that we have x squared first. We're going to be adding this number to the other side. So then that's going to be plus 0.115138 x plus, oops, sorry, actually minus 6.90 times 10 to the -5. And that's going to be equal to 0. Okay, so we're going to need the quadratic formula. Let's see. Okay, so we go ahead and enter our values. We hit calculate. And we get x is equal to, so which value am I going to choose?
The positive one?
The positive one. 0.000596. Okay. And then that's going to be molar. And that's also going to equal the concentration of the hydronium ion. So if I'm calculating the pH, how would I calculate the pH?
Is this where you use the negative log?
Right? So pH equals the negative log of the concentration of the hydronium ion. So in this case, negative log of, I'm going to put in scientific notation, 5.96 times 10 to the minus 4. I'm going to take the log of that. Okay, and negative log of that is going to be equal to 3.22. Okay, how you guys doing?
So far, pretty good. So
Okay.
far.
Yeah. So it's pretty simple, right? It's just like, it's still the same major concept. Only thing we're applying it to a weak acid and a weak base. And so you're just kind of spiking the situation. Does that make sense?
Yes.
Okay. Okay, so I'm going to let you guys work on the problem below it once I get there. Okay. Oh, let me take a step back though. Oops. Okay, so in this context, it's going to be the same type of concentration that you're doing, and instead you're actually going to work with that molarity to calculate the number of grams. So you just have that one extra step. Once you get the molarity of the solution, you're going to sit there and use the number of milliliters to sit there and calculate the grams that you have. Does that make sense? So it's using what you guys already know. So it's just that one step further. So if you kind of notice that this semester has been pretty much using all the things that you already know, writing the chemical equation, figuring out the number of moles, knowing the concentration, you know, the only thing that we add just a little to it, right? It's just adding these equations, right? Okay, so your buddy kind of has its own buffering system. So your pH is about 7, it's between 7.2 to 7.4. And what kind of keeps your pH the way it is that our body has a couple of things, or a couple of homeostatic systems. One of them is the bicarbonate. So like our stomach, we basically use acetic acid, hydrochloric acid, not acetic acid, hydrochloric acid to help us dissolve peptides or protein. And so that happens like as it goes to the stomach. So that happens in the stomach. As it goes to the intestines actually neutralize the acid so it doesn't destroy the intestinal wall. And it uses the bicarbonate to neutralize the intestinal wall. And so we also have the phosphate buffering system, because a lot of our nucleic acid use phosphates, and then also in terms of ATP, adenosine triphosphate, it uses those phosphates. So we have a lot of inorganic phosphates around to help buffer our blood system. And then we also have blood-soluble proteins that also help in that regard. And lastly, we have the kidney that's going to be actively filtering the blood itself to try to make sure that we maintain a consistent pH. If our pH is off, it can cause serious damage to the inside of us, major heartburn, okay, kidney failure, So we have to try to maintain that 7.5 pH. And this is essentially how it does it. It sets up that equilibrium, okay? Are you guys clear on that? You get it?
Yeah, I have a question.
Okay.
So I heard in the bio class I took a while back that how there's like alkaline waters and all that. That's pretty much a scam, or it doesn't work. Is that true, or?
So it does work to some extent. It depends on what you're using the alkaline water for. So the pHs that of a lot of the alkaline waters, the initial pHs that a lot of them are, they're going to be around 7.4. So they're just slightly at the same level as your blood, right? So you're basically putting in the same solution that your blood is normally at. So you're not giving or taking it. You also have more recently pH water that is going to be like 9.5, which is essentially what I drink. So it really depends on your circumstances. So I have bad issues with heartburn, right? So that basically means that a lot of my heartburn is a result of high acid production in my stomach system. So we're kicking out a lot of the hydronium ions, right, or H pluses. So my body is actually, because it's not in a very nice balance, my equilibrium is a little bit off, my homeostasis is off in that context. I have a lot of acid being produced, and so I get really bad heartburn. So the water does a little nice job of kind of not completely neutralizing the heartburn, but it tempers it. So it's a little bit better. But the ones that are around that 7, you have 7.2, 7.4. So those typically, they're not going to be doing too much for you anyway. They're about the same pH as the water that you drink from the tap, particularly if you're in Kalinga. Kalinga's water is actually, Kalinga's water is actually 6.8. So it's a little bit lower. Hanford's water is about 7.2, 7.4. So it's essentially tap water. But yeah, in a sense, some of them are getting over. Good question, though. Okay, so, and now we're going to be talking about the pKa. pKa is just the minus log of the Ka. So if we have our pKa, we can plug in our value. What is the generic equation? The generic equation for Ka? Ka equals, again, products over reactants. If we had a generic acid, it's going to be the conjugate acid, concentration of the conjugate acid, times the hydronium ion over the base. Over, okay, let me rephrase that. We have the conjugate base times the hydronium ion over the acid. And get ahead of myself. Okay, so we substitute this in for our Ka, we get pKa is going to equal minus log concentration of the conjugate base times hydronium ion concentration divided by the acid. So, oops, that does not look pretty. You guys mind if I move this?
No.
It lets me. Okay, so if we work this out a little bit further, we'll get pKa equals, we know that when we have two things multiplied by each other, it's the same thing as saying we're working with log minus log concentration of the hydronium ion minus log concentration of A over HA. Okay, so then I could say pKa is equal to, this is just pH minus log the concentration of the conjugate base over the acid. Okay, so if I wanted to solve for pH, so I can just say pH is going to equal pKa plus the log over the concentration of the conjugate acid over, conjugate base over the acid. Okay, so if you guys remember the numbers from that last problem that we did with the lactate, so if we had lactate acid, La, the La was, that was 0.500 molar, the lactate. That was 0.115 molar. And then if I remember correctly, the pKa, the Ka was equal to 1.38 times 10 to the minus 4. Is that what you guys got in your notes? Yes, no, maybe? Are you there?
Oh, yes. Yes.
Okay. Okay, so do me a favor, take the log of the minus log of the Ka. So we're going to calculate the pKa. So in this case, it's going to be minus log of 1.38 times 10 to the minus 4. What do you guys get?
I got 3.86.
Okay, 3.86. Okay, so we have pH. So it's, oops. me clean this up. So we'll plug that in there. So we have 3.86. Okay, plus the log of 0.115 over 0.50. Okay, so we'll get so I get pH equals 3.86 minus 0.638. So then I get my pH is going to equal 3.22. Is that the same number that we got the last time?
Yes.
Yes. So in other words, rather than doing the whole ice table, what I could have done is just plug it into this is called the Haasenbach equation. We could plug it into the Haasenbach equation and then just solve directly. The Henderson-Hassenbach equation. Okay, do you guys get that? You see the benefit of it?
Yeah.
Okay, so the only thing is that we're making an assumption with the Henderson-Hassenbach equation. We're assuming that we have roughly, it's going to be less than 0.5, less than 5% change. Okay, so if it's less than 5% change, we're going to be okay in terms of the change of the acid to the I should say the acid to the hydronium ion. Okay. Okay, so this is just a graph just showing you what I just talked to you about, the whole thing with buffering. So you guys get an idea. It's like here we're adding, this is a 0.1 molar sodium hydroxide, which is a strong base, and adding 10 mils of it, 20 mils of it, 30 mils of it, and we're only getting a change of 1 pH by adding so much to it. So that means that that system is really buffered. And then it's not until you get to what we call the equivalent point, go beyond that equivalent point, and then that's when you get the dramatic change. Okay. This here is just showing you the Henderson-Hassenbach equation after I just calculated for you. So it's using this equation that we just calculated. So you saw how it was actually formulated. Let me clear. So when we talk about acid-base titration, acid-base titration is basically trying to get to the point, the equivalency point of that acid and base. So if we're working with a weak acid and a strong base, we're adjusting that acid so that we get to that equivalent. Okay, that equivalency is represented by a state of equilibrium itself, that we get that complete neutralization. Okay.
Dr. Henry?
Yep.
Can I see that last slide real quick?
Yep. Maybe. If my computer lets me. Oops.
Okay, thank you.
This one here.
Yep, I got it. Thank you.
Okay. Okay, so let's use the Henderson-Hassenbach equation to calculate the pH of a solution with a 0.121 molar lactic acid and 0.428 molar sodium lactate. Ka of 1.38. So we already calculated our Ka earlier. So what is our pKa for that? Again. Is that right?
3.86.
0.86. Okay. Okay, and so then we'll have Haasenbach equation says pH equals, you guys can help me out here. I'm old. Alexandria, you gonna help me out? Gonna leave me high and dry. So Mauricio helps me out. Thank you, Mauricio. Of our conjugate base. So in this case, it's just going to be the lactate. Over galactic acid, concentration of galactic acid. Okay. So we just go plug it in. We have 3.86 plus the log 0.428 divided by 0.121. .41. Your value for the pH. You guys get that?
Yeah.
Okay. So you saw how fast we turned that around compared to what we had to do with the ice table and then quadratic formula. And so some benefit. Yes, no, maybe. Okay. Okay, so I'm going to go ahead. So when we talk about titration, it's just, again, you're going to be adding enough acid to kind of get the equivalency point of the base, okay, or vice versa, okay? And so under those circumstances, then you're just going to sit there and in the case of a weak acid, do you guys remember a weak acid and a strong base? Is that going to be, is your equivalency point going to be greater than 7, 7, or less than 7? Your pH for your equivalency point. Weak acid, strong base.
Would it be greater than 7?
That's right. And so if it was a okay, so in this case, we would expect this the pH for this to be greater than 7, right? Did you get that? Okay, so I'm not gonna go ahead and calculate this. I'm gonna leave this for you guys to calculate, because I want to try to get to the next chapter. But I do want to go over one more other thing dealing with acid and bases. So in the case of acid and bases, we often use acid base indicators. You guys were supposed to be using the cabbage, red cabbage indicator. Only thing I think I got ripped off with the red cabbage indicator. So a lot of the indicators that we use, they're dyes that are basically extracted from plants. And like particularly the red cabbage indicator, it has a very wide range of a color change. So it's chromatic. It changes color based upon the pH that it's at. I know I do, so let me see. I know where it's at. Okay. So this is what, if the red cabbage was actually working correctly, this is what you'll see, right? So if it's a low pH, you'd have, your indicator would give you a red color, strong red color. The weaker your pH gets, you go from that red to like, I guess magenta, then to purple, then you start going to blue, green, yellow, and orange. Okay, so if you guys ever get an opportunity and you want to play with pHs or anything like that, take some red cabbage, boil it for a few minutes, strain it, and then you basically have your indicator. So that extract was supposed to do that. However, that extract was a knockoff. I believe it was beet and not red cabbage. Okay, so let me get back to the slide. Okay, so these are a table of common pH indicators. Now, these indicators, they're going to be within ranges of pHs that they're going to be active. So like, for instance, the crystal violet, it's between 0 and we'll say about 1.5, okay? So in that range, if you have pH in that range, or if you're going within that range, you're going to be changing from 0 being at 0, it's going to be orange, but then at 1.5, it's going to be blue. Anything in between there, you're going to have that gradient, okay? And so you use these indicators within the specific range of the pH. So you're always using an indicator to sit there and determine. So if your equivalent point is going to be like something, if you have a weak base and a strong acid, and your equivalency point is 6.2. So which indicator would you use to sit there and to help you determine whether or not you're changing? Let's say you're starting with the acid in solution, a strong acid, and then you're going to be changing you're going to be titrating with a weak base. And you're shooting for 6.2. So which indicator would you select?
Would you choose the bromethyl blue?
Okay. So that would be a perfect indicator to choose, because if your pH is somewhere, within this range, So any of these indicators here would actually work, right? So you'd be hitting that tail end of the, what is that, erythrochrome black tea. So bromocrest purple would work. Alizarin would work, and the bromothiamyl blue would work. So either three of those would be the ideal ones for that. Simple.
Yeah.
Okay. Okay, so that's all about acid to base equilibrium. Now we get to talk about solubility, and that's going to be our last topic I can get out. That I'm covering this semester, unfortunately. Okay. Okay, so we have at this point, we've gotten used to using that equilibrium equation. It hasn't changed at all, has it? Yes, no, maybe?
No.
No, it's consistent. It's always going to be products over reactants, right? So that's not going to change when we start talking about solubility. KSP represents the equilibrium constant for solubility. The way it works is that you basically have a solid that we're going to be putting in solution. And as we put that solution in solid, it's going to form an equilibrium. There's going to be so much of the ions that are able to be dissolved in solution. Even things that are quoted nearly insoluble, you're going to have a small amount of ions that are going to be able to come out of it. Okay. And so that equilibrium constant kind of dictates how much of it is going to be able to go into solution. Okay. So if we look here, we have lead bromide, right? So lead bromide is going to get ionized and become lead 2 ion plus bromide minus ion. So, and then balancing it out, you need 2 of those bromides. Now, the equilibrium constant equation is going to be KSP equals the concentration of the lead ion and the bromide ion squared, because we know that solids and liquids aren't going to play a part in the equilibrium. Okay, only aqueous solutions and gases, right? You guys remember that? Are you with me? Thank you, mothers. Okay, so here it's known that the KSP for lead to bromide is going to be 6.60 times 10 to the minus 6. So that's going to basically indicate a low solubility compound. Okay, and meaning that not too much of it is going to be soluble. A lot of it's still going to be left over in that solid. So we would say this guy is nearly insoluble. Okay. Are you with me?
Yes.
So if you have a high K value, that basically means that everything is pretty much soluble, right? If you have a low KSP value, then that means that most of the stuff is insoluble. Okay? And that makes sense, right? Because if you have a larger value for these concentrations, your K SP is going to be a big number, a bigger number. Okay, so let's talk about how you're going to use this. So in this situation, you're basically getting equilibrium with your solid and your ions. And so that equilibrium constant lets us know how much of that ions we can actually get in solution, how much of it is going to be soluble. And so the first thing that we always want to do is, of course, get our balanced equation. We already have that. So then the next thing would be to do what? Says, the question asks us, write the equilibrium equation and calculate the KSP for magnesium hydroxide with magnesium ion equilibrium concentration of 1.31 times 10 to the minus 4. So what are we looking to solve? We're looking for the KSP, right?
Yeah.
So KSP is going to equal what in this case? Okay, good. So what we'll do is I'm going to put you guys in a room and then I'm going to let you guys work it out. You come back with an answer. How about that? So take a snapshot. Everybody got a snapshot?
Yeah.
Good. Okay. I'll give you guys, I'll take it 10 minutes.
Yeah.
Okay. So it'll be 10 minutes. Let me see. Breakout room. Maybe. Rooms are open. Oops. Wait, actually, let me close it and let me fix that 10 minutes. Rooms are open. Yeah, stay around. I need to talk to you.
All right.
It didn't let me join the room. It like brought me back here.
Try it again. It should be open again. Okay, Jess. Are you there?
Sorry. Can you hear me? I accidentally went.
I know. That's why I pulled you out. Okay.
Okay.
We lost somebody. 1, 2, 3, 4, 5. No, that's right. 6, 7. Okay, so you may be getting contacted. I should probably tell you first. Mrs. Kumari is not going to be teaching the summer course.
All right.
Okay. So instead, I may be teaching the summer course
Oh, for the high schoolers?
for the high schoolers. Yes.
Okay. I am okay with that.
Yeah. So the way we're going to do it is they're going to go to the lecture online, and then they're going to go to the lab 2 days a week.
Okay. So then. So they're gonna go to the lecture from Kalinga, right? The original lecture that you would have?
Yeah, that we're going to be doing online. Yeah.
Okay.
And so what we're going to have them do, they're going to come to campus, and then they're going to be interacting via Zoom And we're talking about having you there to sit there and kind of guide the lecture while I give the lecture.
Okay,
Okay. How do you feel about that?
that's fine. I'm okay.
Okay. And so,
Sorry, go ahead.
yeah. So, so you may get some more hours, in other words. Are you okay with that?
Yeah, I'm okay with that.
Yeah. So, because I think they can top you out at 24 a week.
Okay. Yeah,
And
yeah.
then
They stopped me at 24.
they stop you at 24. Yeah.
Yeah.
Yeah. So, and I may be able to negotiate Cole, since I can't, I'm going to be at 2 different places. I'm going to need Cole to be in Coalinga at points too. So,
Okay. So
So-
just to be sure, so that everything is going to be in Coalinga, right?
no, everything except the lab. We're actually going to be doing it at the high school. So,
Oh,
yeah, so we're setting it up. What we're going to do is we're going to set up, do the lecture. Lecture is going to be Monday, Tuesday, Wednesday, Thursday. And then, and then you're going to help them get the lecture all set up on the days that I'm not going to be there.
oh, I see. Okay.
You understand?
Yeah.
Yeah, and so, and then I'm gonna see about getting Cole or Coalinga to be the SI to kind of dictate, help with the lectures there. Try to get him some extra hours as well too.
Okay. Okay. Yeah, that works out.
Okay. So,
Because Cole and I talked to Catherine this week. So, but she wasn't sure about Miss Kamari, but
yeah,
I guess things are starting to get situated.
yeah, Mrs.
So,
Kamari
yeah.
actually has to go to India this summer,
okay.
so, yeah.
Hmm.
So as
Okay.
of right now, I will be teaching the class, so. But that could change any moment now, so.
Yeah, okay. Yeah.
Okay,
Yeah, that sounds good. Yeah, because last summer everything was kind of like a mess.
Yeah.
Where I didn't know like what I didn't even know what hours I had to work.
Yeah.
And that's why Paul and I were trying to get everything set up before the summer session starts so we can like get up and running.
yeah,
But yeah, that makes sense.
Yeah.
So I guess I'll have tutoring for yeah, Cole and I will just have to talk as well. So we can split the more hours between both of us for upgrade.
yeah.
Okay.
So how many hours were you guys getting before?
Catherine told us 12 hours for chemistry.
So what I'll be able to do, let me
but I
talk
don't-
to Rebecca. I love hearing my Rebecca.
Okay. Because tomorrow, the summer session team is having a meeting for summer. I don't know if you would like to join or if you have stuff going on.
I have the 2A's presentations all day, so it will be.
Okay.
Yeah, it's been
Okay.
crazy. This has just been. These staggered
Yeah.
courses, they're good, but they're bad. But I just need to make sure that they're more staggered than what they've been, right? So I need to start at the beginning of the semester so that one ends 2 weeks earlier than the other. So It's just a lot.
Yeah. Yeah. And did Hartnell, did they end already or?
No, they're ending this week. So they're ending this week and 2A is ending this week. So
Okay.
I kept them on the same schedule, so.
Okay. Yeah.
It was painful.
Yeah. You're teaching way too many classes, Dr. Henry.
Oh, yeah. Like I said, I did it to myself in a lot of ways. I made 2 sections for each one because initially that's what we were going to do. Then they canceled the 1B other section. So then there was only really 1 section. So, and that really hurt me. So,
Yeah. And during the summer, are you just teaching chemistry?
yep,
Like, is that the only? Okay.
just 2A. That's it.
Okay.
Yeah. Yes, no biology, no. Yeah, so it'll be all of them. They're all going to put them all, merge them all in the same class. So.
Yeah, I think that's better.
Yeah. Yeah, so it's a total of 25 students. So it's manageable.
For the summer?
For the summer. There's 15 because the way with COVID, still, we have 15 that'll be on campus here and 15 that'll be 10 that'll be on campus in DC. So.
Okay. And for Avenel, do you know how many students are going to be taking?
I think there's 22.
Oh, okay.
Yeah, but their classroom can actually hold 40 students. So.
Okay.
Their science classroom. Yeah.
Okay. And are the students going to have the option to like Zoom in through their home, or are they going to have to actually go to the school and I'll like
I want them to come to campus.
Okay.
Yeah.
Okay.
I don't know how do you feel about that?
That's fine, as long as yeah, we follow the guidelines and everything. I'm okay with going to campus.
Okay.
Yeah.
And what I'll do is, like, since we're gonna have classes, there's gonna be 2 days in Coalinga, 2 days in Fireball. So what I'll do is I'll do 1 day in Coalinga, 1 day in Fireball. 1 day in Coalinga, 1 in Avenel, and so we'll mix it up like that.
Okay. Okay. Yeah. Okay. Sounds like a plan. And we're not, just to be sure, we're not meeting this weekend, right?
No, we're not gonna meet until after next week. So.
Okay.
Yeah. So the 28th is my sister's. Excuse me, 28th. 29th is my sister's birthday, so we won't be able to do it that weekend either, I guess, unless we do it on a Sunday, which we can do.
Okay.
As we're up for it.
All right.
Yeah, this weekend is just too bad for me. I have too much grading to do. So.
Okay.
Okay, you guys are back. Good. Excellent. So you guys can start working on the board. Explain this problem and what we need to do to get there.
I think we were just kind of confused because we were only working with one number.
Oh, okay. So are you saying that you guys need a little more guidance?
Please.
Okay, that'll work. So let's start off with the very first part. What is the equilibrium equation?
Is it the equation that's on the board already, or do we have to write like a separate one?
Not the chemical equation, the equilibrium equation. The equilibrium equation is for the equilibrium constant. The equilibrium constant is going to be equal to what? KSP is going to equal what?
Is it like brackets magnesium +2?
Okay,
And then close that bracket, and then another bracket of OH negative, and then the exponent of 2.
that's right. Okay, so that's going to be the equation that we're going to be starting off with. Okay, so they tell us if we do that ice table, so here we don't have to worry about this guy because it's solid, but we do have to worry about these two. So we have magnesium ion, and we have the OH ion, right? So initially, they tell us that we have 1.31 times 10 to the minus 4th magnesium. Now, you guys remember what molar means? What are the units for molar? Molarity. That M, when I say 1.31 times 10 to the minus 4 molar, what does that mean? What are the units?
Moles over liters.
It's moles over liters, right? So in other words, we're saying that we have moles over liters of solution. So this is solution, which is everything, but we have moles of our solute. So in this case, it will be moles of our magnesium ion. Okay. So if I want to change my moles of magnesium ion, trying to figure out how many moles of my hydroxide ion, how would I go about doing that?
You would use the mole to mole ratio.
I'd use the mole to mole ratios. For every 1 mole of my magnesium ion, I have 2 moles of my OH ion, right? So right now I have 1.31 molar, 1.31 times 10 to the minus 4 molar. So if I multiply that times 2, I would get what I'm actually starting out with my hydroxide ion. Is that true? So that would be 2.62 times 10 to the minus 4 molar. Okay. So by the way, this was at equilibrium. That was my mistake. So then we're saying it says that was the magnesium ion at equilibrium. So by default, because when this guy gets to equilibrium, it's going to also make the hydroxide, but it's going to make twice the amount of hydroxide that it's going to make of the magnesium ion. So if I want to solve for my Ka, now all I need to do is plug it in, right? I mean, not my Ka, my KSP. All I have to do is plug it in. So I get KSP equals 1.31 times 10 to the minus 4 times 2.62 times 10 to the minus 4 squared. And what do you guys get for your KSP?
8.99 times 10 to the negative 12.
Okay. Piece of cake.
Yep.
Okay.
So Dr. Henry, in this case, you just had to use the multiple ratio for the hydroxide.
That's correct.
Uh,
Yeah.
I was there like struggling. Where's the other number?
Yeah, because I mean, it's just, you have to think about it. You're putting in this powder, right? And you're putting it in water, and then you're letting it sit, and it's going to get so many ions in solution that is going to be the equivalent of your equilibrium constant. But that means that that powder you have the ionic compound together, but some of them are going to dissolve, right? Only a few of them, not too many of them, are going to dissolve. So the amount of, excuse me, the amount of magnesium ion is going to be half the amount of the hydroxide ion, always. So you're going to need 2 times the amount of hydroxide for every 1 magnesium ion, right? Because when you have to think of it as it's coming undone. Make sense?
Yeah, and on this one, you don't have to worry about the product over reactant thing because you focused on the products.
Well, you don't have to worry about the product over the reactants because the reactant is a solid.
Okay.
So in that case, that reactant is always going to be like a concentration of 1, right? It's going to be perfect. You're not going to have anything else. So you're never going to take a solid into consideration. You're never going to take a liquid into consideration, right? So the only thing that you're taking into consideration when it's aqueous or if it's a gas. Does that make sense?
Yeah, so just aqueous and gases, right? Okay.
Okay. It says, okay, so when we talk about molar solubility, so the molar solubility is what you're actually calculating for your ions, right? So it's when you get the concentration of how much is going to be in solution normally, how much is going to be soluble. So that's going to be your maximum solubility, right? So you get your equilibrium constant. That constant is going to dictate how much the concentration of each of your ions are going to be in solution. That's going to represent your molar solubility. Okay. Does that make sense? Okay. Now, so what does that molar solubility mean? So molar solubility basically means that if you go above that concentration, then you're going to start producing that precipitate. So if you go below that, then it's going to stay soluble. Okay. So the molar solubility is that equivalent point where you have the solid and the ions. Okay. Does that make sense?
Yeah.
Okay. So if we were going to calculate the molar solubility for lead 2 bromide with the KSP of 6.00 times 10 to the minus 6. So all you're going to need to do is set up our equation. KSP is going to equal to what? First,
Magnesium.
what was that?
Magnesium 2 plus.
Okay. So, well, you mean lead?
Yeah.
So lead 2 plus. And
What do we use? The bromide.
Concentration of bromide, and that's going to be squared because we're using this equation now. Okay. Okay, so if we sit there and if we defined X as being lead, right? Concentration of lead, then we could sit there and substitute Pb2 plus is going to be X. Then bromide is going to be equal to 2X, right? Is that true? Since you're going to get twice the amount of bromide for every one lead you get.
Yes.
Okay, so then I can plug that into my equation. So then I get X 2X squared. And we know that that's going to be what, 4X cubed. And that's going to equal our value, KSP, which is 6.60 times 10 to the minus 6 equals 4X cubed. So then X is going to equal 4. What did you guys get for X? Are you there?
Okay, I forgot how to cube root on the calculator.
I think it's a shift, and you'll have cubed, and then if you hit shift, cube root would be that shift, and then you hit answer, and then it'll give you the, depending on the calculator you have, of course. Are you there? Yeah,
Yeah, I'm here.
you're here. You guys are using keys that you haven't used in a long time, huh?
Yeah.
Okay. So, you guys get it?
Yeah, kind of.
Okay, so I'm going to go over one more thing. I know we're out of time, but okay, so like we were talking about Le Chatelier's principle, we have what we call the common ion effect. Okay, common ion effect is just a special case or Le Chatelain's principle. So if you guys remember Le Chatelain's principle, it basically says, you know, if I'm putting in something that's in the product side, it's going to shift the reaction to the reactant. And if I'm putting something in on the reactant side, it's going to shift the stuff to the product. Okay, so the first question here is, if we have an equation where we're precipitating silver chloride, okay, so here's our silver chloride, and then so this is your equilibrium concentration for the solubility of silver chloride. So determine the effects of adding silver nitrate to a solution of silver chloride. So what's going to happen there if we're adding silver nitrate to it? Which way are we going to shift our reaction? So let me give you guys a little hint here. Nitrate, anytime that nitrate hits solution, it's going to dissolve, whatever it's with. Doesn't matter what it's with, it's going to always dissolve. Nitrate is just kind of like, it's the guy that you're bringing to the party just to go to the party, right? So that guy's just going to be a spectator, okay? So in this case, you're just adding in what? What is going to be, you're adding in this situation to your concentration of silver chloride?
Nitrate.
So again, nitrate is the spectator. Do we care about nitrate? He ain't going to do nothing
No.
for us. We don't care about the nitrate. So who do we care about?
The silver.
The silver. So if I'm adding silver, I'm adding in more silver, which way is the reaction going to shift? Are we going to go towards the products? If you're putting in this, now remember, it's at equilibrium now. It's perfect. Which way are we going to shift to try to get back to equilibrium? The reactants, that's right. It's going to shift in this direction, right? So if we're adding in our products, it's going to cause the reaction to go the other way. So that's going to sit there and bind. So let me give you an example. It's easier if you see it. Seeing is believing. Okay, so this is my cup. Let's say in solution, I have my silver. And then down here, I have my silver chloride. And right now, it's in equilibrium. So we have 3 that are in silver in solution, and then 3 that are going to be in silver chloride. Give me a second to get my chlorides up. Oops. Okay, it's an equilibrium, right? So they're happy. So you got it at that perfect concentration where you have your free silver up here and your free chloride up here, your free silver up here. So as soon as you add that silver, it's going to try to get back to equilibrium. So if I add that extra silver here, it's going to try to find a way to get back to equilibrium. So the first thing that it's going to do is it's going to try to grab that chloride and bring it down to make silver chloride, right? Because it's going to shift it towards that other one, try to find a way back to that perfect balance. Does that make sense?
Yeah. So it's like a seesaw, kind of.
Yes, it is exactly like a seesaw. So equilibrium is the point where you both weigh exactly the same, right? And then if somebody comes along and jumps on the other side, you're gonna have to try to get somebody on the other side to sit there and do it, right? So then you're gonna favor that other side. You're gonna be pushing something to the other side. Okay.
Okay. Yeah.
Okay, so determine the effects of adding sodium chloride to a solution of silver chloride. Okay, so again, this guy is just bringing the guy to the party, total spectator, not going to do anything. So what's going to happen with chloride? So what's going to happen in the case of the chloride? So now we're increasing the chloride. What's going to happen? Which way is the reaction going to shift?
To the right? Or to the products?
Okay, so again, you're doing exactly the same thing that we did with the silver, right? You're adding silver ion, you're going to be shifting it back to the reactant, right? Here, you're adding chloride, you're going to shift it back to the reactant. So anytime that you make it unbalanced, it's going to try to find its way back to being balanced. You're putting extra over here. So it's going to cause this reaction to try to go the other direction to balance it out. Does that make sense?
So the shift is like the side that you have to balance out for
Yeah.
it to be equal. Oh, okay.
Yeah, because you're adding more. Okay, so it's kind of like you added a friend over to the side. So now what you did, you have to balance like this, the seesaw, like this, right? So normally it's like this, it's balanced. This is our seesaw. That's equilibrium. Now what you've done, you've added more people over here or more weight over here. So what are you going to do to sit there and get it back to balance? So now we have something like this. What are you going to do to get it back to balance?
Add on the other side.
That's right. So then to get it back to balance, you need to add to the other side, right? So you're going to be shifting to the other side. Does that make sense?
Why does it start out on the product side?
It starts off on the product side because we have sodium chloride. Sodium is it doesn't do anything. So as soon as sodium chloride hits solution, that salt, it dissolves, right? So then all you're adding is a Cl minus. So you're adding more Cl. You're just adding some extra Cl. So in other words, you're adding more on this side to kind of push it down, like we did here. So, and now we want to try to figure out a way to get it back to balance. The only way to get it back to balance is if either we add somebody over here, right? So we're going to shift it towards the product or add more product, right? One or the other. Does that make sense?
Yeah.
Okay, so what's going to happen if I add more silver chloride, metal, solid? It's going to shift to the products. Okay, you guys get that? So again, this is just a special case of Le Chatelier's principle. That's it. Okay, let's see. One last thing that I want to talk about is Lewis bases, Lewis acid and Lewis bases, real quick. So up until this point, we've defined acids two different ways. We defined it according to Arrhenius, which is basically saying, oh, it has H plus, or an OH. We've defined it as Bronsted. Bronsted is, it's, excuse me, it is a proton donor. Acids are proton donors, bases are proton acceptors. Now, Lewis basically said that acids are electron acceptors and bases are electron donors. Okay, so it's a little bit opposite. So in this case, we're going to be looking at the electron. Where are the electrons going? Okay, are they going, if they're going to, acids are going to be accepting the electrons and bases are going to be donating the electrons. Okay, okay, so here, who's going to be the acid and who's going to be the base? Okay, acid, base. Good job. Okay, what about on the second one? Who's going to be the acid? Who's going to be the base?
Is BH3 going to be the acid?
Okay. And water is going to be the base. Yep, because BH3 is going to be accepting the electrons from the O2 minus. That's going to be heading over. Okay. What about here? Who's going to be the acid? Who's going to be the base?
Water is going to be the acid.
Okay. Okay, you guys get it?
Yeah.
Yeah, it works. Okay. Okay, so we're going to stop here. So you guys are going to be responsible for KS solubility and be familiar with Lewis acid bases. So on your final, real quick, on your final, we will, any questions that, let's see, any questions that, or any topic that we didn't go over, you guys, if you answer those questions are going to add towards extra credit points. Okay. And then, but they're not going to count against you. Okay. Yes. So any topic that we haven't gone over, if you continue to do the Chem 101 homeworks, they're going to count towards you. So we're going to stop at solubility, the KS solubility. Any extra homework that you've done above that will actually be added as extra credit towards your homework grade.
Are we still able to turn in labs too that
Yes,
we might have missed?
yes. You should be able to turn in. I think we have it set up that all the labs are due on the 21st. I mean, on the next week. Is that true, Jessica? Or am I lying?
That's true. They're all due on the 21st.
On the 21st, this week, this Friday.
Yes, this Friday.
Yep. Sorry, it's all a big haze. Any other questions?
I have a question on the final, but I mean, it doesn't really. I was just gonna ask you something about the final, like the location and stuff.
The location is going to be in N3 in the Chem room.
On Wednesday or Thursday?
I'll let you know the time and date exactly. I have to take a look at that. I'll email it to you. So it's going to be based upon the calendar that you guys sent out. You guys all responded, right?
Yeah.
Yeah. So it's going to be based upon that. So it's going to be the time that I could get the most people at one point, or at least 2 sets of people at one point. Okay.
And it has to be in person, or it's because
Yeah,
I'm really in Sacramento and
you're really in Sacramento?
yeah.
Yeah, as of right now, it has to be in person because the test is the ASC exam. And so I can't let it out of my being
Okay.
right now. Let me figure out something, and maybe we could come up with a solution. Okay.
I mean, if anything, if you can't, I mean, I can make it. It's just slightly inconvenient for me, but I'll be able to in person.
Yeah. No, I get that. I get that. But as of right now, the test has not arrived. So there is a possibility that things may change. I will know probably the day of or the day before.
Okay.
So, but I'll let you know as soon as I get that. I have to take a look at your guys's. Do that now. Your doodle.
Thank you.
Have a good
Great.
weekend.
Bye.
Take care, Dr. Henry.
Okay. Bye-bye.